Okay, so let's start from here. Uh, Earlier we discussed about the trapezoidal rule. Uh, now now there is another rule which is called as the Simpsons rule, and these rules are for the finding the integrals. So Simpsons rule is more accurate than the trapezoidal rule. In the trapezoidal rule, we assume a straight line between 2 points. However, in the Simpsons rule, we try to establish the points based on the second order or third order polynomials. So more accurate estimate of an integral is obtained if a higher order polynomial is used to connect the points. So the formulas that results from taking the integrals under the second and third order polynomials are called Simpsons rules. So Simpsons rule have is of two kinds: Simpsons 1/3 rule, 1/3 rule, or Simpsons 3/8 rule. Simpsons 1/3 rule uses a second order integral, and when Simpsons 3/8 rule, which we'll see later, uh, considers three third order polynomials. So when there is second order polynomial, then that means we will need at least 3 points on the curve to establish the rule for that area. So we will need 3 points. And similarly, if there is a third order polynomial, then we will need at least 4 points. Okay. So Simpson's 1/3 rule results when a second order interpolating polynomial is used. So let's see them here. The difference between the Simpsons 1/3 rule and the Simpsons 3/8 rule. So the Simpsons 1/3 rule takes 3 points, whereas Simpsons 3/8 rule takes 4 points on the curve, okay, to establish the polynomial. So the established polynomial is represented by this dashed line, okay, and the area under that established polynomial has been shaded. Similarly here, this polynomial is here. So this is the difference between the Simpsons 1/3 rule and the Simpsons 3/8 rule. So accordingly, their equations or their formulas will be different. So how to establish these formulas? So just as we did in the trapezoidals rule, we will equate the general form of the integral with its approximate form. So in this case, the approximate form will be the second order polynomial represented by this f sub 2, okay, x, so from a to b. And then this f sub 2 can be represented by a Lagrange polynomial of second order. So you will know that in the interpolating factor, we can represent any polynomial into its Lagrange uh, uh, type, in which you have the coefficients of the polynomial in the form of these factors and fractions. So x1, x minus x. So this f2 of x can be represented by x minus x1 into x minus x2. So these Lagrange, and then similarly there are other terms. So this is called as the Lagrange representation of the second order polynomial. So, this expression is long, and then it needs some algebra to simplify. So after you will simplify it, the expression will simplify into this form. So this will be the form that you will use for the application of the Simpsons rule. So this form you can use for the application of the Simpsons rule, and then you can see that in this form, this is one application of the Simpsons rule. You can see that there are three terms. So this is in contrast to the trapezoidal rule where there were only two terms. Okay, so here there are three terms for the one application of the Simpsons rule. In the first term and the last term are multiplied by a coefficient of 1, whereas the middle term is multiplied by a coefficient of 4, and then the whole sum is divided by 3 and then multiplied by h, whereas h is equal to b minus a divided by 2. So h is equal to b minus a divided by 2 in this case. Okay, so so this is one application of the Simpsons 1/3 rule. Similarly, it's this is called as the single segment application of the Simpsons 1/3 rule. Has a truncation error of et is equal to minus b minus a power 5 over 2880 fourth derivative. Okay, f4 means the fourth derivative at some value of psi between a and b. Okay, at some value between a and b. So Simpson's rule is more accurate than the trapezoidal rule. So as we will see later in the example. So this, let's apply this single application of the Simpsons rule. So what is this application? We will apply it to find the area under this curve, which is represented by this equation. Fx is equal to this fifth order equation from a is equal to 0 to 0.8, which is the same as in the previous examples. So in this case, we already know the exact answer, exact integral, which is 1.640533 up to the 6th degree of decimal places. So by the Simpsons rule, we will need 3 points. So first point is a is equal to 0. The third point will be b is equal to 0.8. So we will take one middle point from 0 and 0.8, and then we will have 3 points. So the middle point will be 0.4 between 0 and 0.8. So accordingly, we can find the you can evaluate this function at 0, 0.4, and 0.8. So we will find these the values of the functions will be 0.2, 2.456, and 0.232. And now we can apply this into the formula. So first value 4 times the second value plus the third value divided by 6. Why 6? Because in this case, so you can see that this is h by 3, and then it is b minus a by 2. So b minus a is 0.8, and then 2 from there and 3 from there, that will be 6. So the alternative form, for example, the alternative form of this Simpsons rule is also like this. So instead of representing by h over 3 and then over 2, so there's 2 from here and 3 from here can be combined into h as well. So this is an alternative form for the Simpsons rule. So by applying this alternative form of the Simpsons rule, we get that the answer is 1.367. So 1.367 is about 1 point, minus 1 point. If we will subtract it out from 1.64, 60533, which was the accurate answer. So we get an error of 0.27. So this gives us a percentage error of 16.6%. So now if we compare this percentage error with that which we obtained for the trapezoidal rule, when we applied the trapezoidal rule in example 21.1, over there I remember the error was 89 point something percent. So from the error reduced from 89% to 16%. So which means that one thing we can say that in this case, this trapezoidal, Simpson's 1/3 rule is much accurate than the trapezoidal rule. However, as you can see that still there is this 16% error, which is quite a lot. So as we did in the trapezoidal rule, we normally apply the trapezoidal rule with the multiple applications of the multiple segment application of the trapezoidal rule. So the same we can do with in the Simpsons rule as well to reduce this percentage of error. So going forward into this same example, if we want to find the approximate error, so the approximate error we can find from the here. Okay, approximate error we can find from here in this equation. So simply we will input the values into this equation. Input the values into this equation and then find the fourth derivative. So if we will find the fourth derivative, so then that we can see that this is a simple polynomial. So for the fourth derivative, we will have only which terms left. So this will finish, and fourth derivative, this term will be 900 minus 900. So it will be minus 900. And then this last term will be 400 times 5 times 4 times 3 times 2 x. So it will be like that. So if you will find the fourth derivative of that, this term minus 900 x power 4, so it will be, then you will evaluate it at the middle value. So for example, at the average value, so the average value for this we can find by this formula. Okay, and then you can find that this fourth derivative will be minus 2400. Okay, and then we will apply this. That means the value of f4 psi is equal to minus 2400 into b minus a is 0.8 divided by 2880. So where 2400 is the average fourth derivative for the interval as obtained from this equation, as was the case in example 21.1. So the error is in this case 0.27. So this is the approximate error. Because in this case, because the average fourth derivative is not an exact estimate of this, so therefore this is an approximate error only. Okay, this is not an exact error. So however, because this case deals with the fifth order polynomial, the results match. Okay, so this is how we can find the approximate error. You will need to find the fourth derivative and then its average value by using this formula. So the multiple application of the Simpsons 1/3 rule. So this is necessary to improve the results of the Simpsons rule. So just as the trapezoidal rule, Simpsons rule can be improved by dividing the integration interval into a number of segments of equal width. So it yields accurate results and considered superior to the trapezoidal rule for most applications. However, it is limited to cases where values are equispaced. So yeah, this is the limitation in the Simpsons rule, that the values should be equally spaced. Okay. Further, it is limited to situations where there are an even number of segments and odd number of points. And the second limitation of the Simpsons rule is that we should have the even number of segments. That means the segments which we can divide should be even, 2, 4, 6, etc. Okay, and accordingly the number of points will be odd. So for example, for 2 segments we will need 3 points. For 4 segments we will need 5 points. Okay, so this is the limitation. So if we have 3 segments and 4 points, then we cannot apply the Simpsons rule. Okay, so this is one of the limitation of the Simpsons rule. So here we can see from here the multiple application of the Simpsons 1/3 rule. So it's like that, and then you can say if you take these multiple segments, if we take these multiple segments, so we will see that we can add this first segment, area under the first segment, area under the second segment, and area under the third segments. And then we have, for the first segment, we have x0, x1, x2. For the second segment, we have x2, x3, x4, and then like that. So in here, we will see that this third point will be repeated twice. Okay, so that means there will be a coefficient of 2 with that point. Okay, there will be a coefficient of 2 with that point. Okay, and then the formula will then simplify. So here you can see that if we want to multiply these different points, so then the coefficients, the weights of these multiplications, the weights which will be representing these multiplications will be 1, 4, 2, 4, 2, 4, 2, 4, 2. So the middle points will be multiplied by 4 and 2, 4 and 2, because one of the when we will take these adjacent segments in the Simpsons rule, the first segment, the last segment of the previous, the last of the previous segment and the first of the previous segment will be common. They will be added together. So their coefficient will become 2. And the 4 is from the original formulation of the Simpsons rule. So accordingly, then the formula for the multiple application of the Simpsons rule become like this. Okay, so we will add the first, third, and fifth, or like this odd number of segments, and then multiply by 2. We will add the 2, second, fourth, and sixth number of terms, and we will multiply by 2. So if this is the first term, okay, or in that case, if you represent it by 0, so you can say that the even terms will be multiplied by 4, the odd terms will be multiplied by 2, and the first and the last term will be multiplied by 1. And then we can then divide by 3 times the n, and then multiplied by the width b minus a. So 3 times the n. N is the number of points. So in this case, n should be an even number. If n should be an even number, then total number of points will be n plus 1, because it starts from 0. And then there will be the even number of segments as well. So this is called as the average height in this case. So first 4 times the second, fourth, and fifth, or in this case, I is equal to 135, 2 times the third, fifth, and seventh, etc. And then the last term will be with just a coefficient of 1. Accordingly, the approximate error can be also found by this formula. So in this case, it will be in the numerator, we will have 180 n to the power 4. So here you can see that if we increase the number of segments, so the error drastically decreases, okay, because it is to the n to the power 4 in the denominator. Okay, so let's look at the application of this multiple segment Simpsons 1/3 rule using the same example as before, from a is equal to 0 to b is equal to 0.8. So recall that the exact integral is 1.64053. In this case, let's take 4 segments. 4 segments. So if we want to divide from 0 to 8, so we cannot take 3 segments. We can only take 2 segments, which is of course the original application of the Simpsons rule. But the minimum we can take are the 4 segments. We cannot take 3 segments. We can take 2 segments. 2 segments is just the original application of the Simpsons rule. We cannot take 3 segments. We can take a minimum of 4 segments. So if there are 4 segments, so the first point will be 0. And then if we from 0 to 0.8, if we take 4 segments, so the interval will be 0.2. Okay, from 0.2. So this next point will be 0.2. After that, the point will be at 0.4, and then the point will be at 0.6, and then the last point will be 0.8. So how you will do it? So you will take the first point, the value of the function at the first point, and then the value of the function at the second point. That point will be multiplied by 4. Then you will take the value of the function at the third point. That will be multiplied by 2. And then you will take the value of the function at the fourth point. That will be multiplied by 4. And then you will take the last point. So it will be 0.232. So in this case, then you will divide by 3 times the n, where n is the number of points. So 3 times n, 3 times 4 is 12. And this is b minus a, that is 0.8. So in this case, you will get 1.623467. So which gives a error of 0.017. And now the percentage error has reduced to 1.04%. So remember that earlier this percentage error was in the single application of the Simpsons rule, it was 16.6%, but now it is 1.04%. So this is by taking n is equal to 4. So let's just do it in the Excel to see how it goes. Okay, so this is something else. So for example, if I have this in the Simpsons rule, maybe This one. So this I did in the with the trapezoidal rule. Okay, so this was for the trapezoidal rule. So for the Simpsons rule, we can still start from A, B, okay? And then we can take the values like, so if we take n is equal to say 6, okay? N is equal to 6, so then we will need x naught, x1, x2, x3, x4, x5. So we need these 3 points, these 6 points, x naught, 1, 2, 3, 4, 5. Okay. And these points will be then how we will get these points. X naught will be equal to, because A is equal to 0 and B is equal to 8. So x naught is the starting point, 0. X1 will be x naught plus h. Okay. So in this case, what will be h? So h will be equal to this b minus a divided by this n. N is 6. So it is 1.333. So b was 0.8 actually. Okay, so it will be 0.133. So what will be x1? X1 will be this first previous point plus the value of h. So it will be 0.133. So we get these points. Okay, so this function we evaluated before at this point. So I just copy and paste it, this formula over here. And here we will, we have evaluated this polynomial over here, as in the previous case. This is the same example. Okay, and then I will just copy it down. So we have the values of the functions. So now what I can do for the Simpsons rule, I can add a column for the coefficients. So the first coefficient will be what? Can you tell me what will be the first coefficient? What should I add over here?
1.
Yes, 1, then
4.
4,
2.
2,
1, 2,
4,
and 1.
2, and then 1. Okay.
Mm.
And now what I will do is I will take just this value and then multiply by the coefficient, and then I will get it like this. And then I will take the sum of that. I will get this. And then it has to be divided by, it has to be divided by 3 times the n. Where is n? N is this. And then it is to be multiplied by a b minus a. So what is b? B is this minus a is this. So we get 1.24353. Okay, in this case. So here it is. Here we got the answer of 1.623, but we did not get because our answer should be more accurate than this, because we are using n is equal to 6. So maybe we are making a mistake. So what is the mistake which we are making, which I am making? So that we will need to see. So what was that?
Like x0 starts from 0, but it doesn't end on 0.8 maybe.
Oh, okay. It does not add on 0.8, because how many points I have taken? N is equal to 6. So if n is equal to 6, that means 6 segments. Yes. So there should be a sixth point as well. Yes. So that will be. So there should be. So how many segments I have taken? 1, 2, 3. Yeah, I took actually 5 segments. Yes. So correct. Yes. So I should take one more point. I should take one more point, and then it should be 4 over here, and then it should be 1 here.
Mm.
So then how many segments we have? I have how many points? That means these are total 7 points, and then 7 points will mean 6 segments. So it will be, yeah, it will be 1, 4, 2, 1, 4, 2, 4, 2, and then 4, 1. Okay. So it's like that. Okay, correct. And then in this case, what I got is 1.62. So yeah, we got, I got this point. Now I will add up, sorry, I will, now I will add up these auto sum. Okay. And then now this sum value divided by 3 times the value of n, and then multiplied by the value of b minus a. So now I got it. Now I will get it 1.62685. 1.62685. So where is this? Yeah, 1.62685. So the value have improved. Okay, from n, for taking n is equal to 6, the value have improved. So similarly, we can take a larger value of n, and then we can keep improving the results. So it is 1.62, what we got is 1.62685. Okay, so the estimated error, as we can see that we can find from the formula which was given. And here, this was the example. Okay, so the Simpsons 3 by 8 rule is also there. And the reason for the Simpsons 3 by 8 rule is that it first thing is that the Simpsons 3 by 8 rule is useful when we have odd segment even point formula. So that means Simpson 1 by 3 rule was only applicable for when we have the even number of segments. But for odd number of segments, we can use the trapezoidal rule, but which is not very accurate. But a more accurate rule is Simpson's 3 by 8 rule that can be used for the odd number of segments. So an odd segment even point formula used in conjunction with the 1 by 3 rule is to permit the evaluation of both even and odd number of segments. So Simpson's 3 by 8 rule is not only applicable for the odd number of segments, it can also be applied for the even number of segments. But its application is based on the third order Lagrange polynomial. So for this, we can start from this basic representation of the integrals, and we can represent the function but with the third order Lagrange polynomial. So third order Lagrange polynomial is quite lengthy. However, it can, when we will input over here, and then will simplify it. So the formula becomes like this. So in this case, you can see that compared with the single segment 1 by 3 1 by 3 rule, this formula has 4 terms. Okay, in this 1 by 3 rule, there were 3 terms. Okay, but here there are 4 terms. But fortunately, it is not very. It is not that complicated. It is very rather quite simple. And then you can see that outside of these brackets, we have the 3h by 8 terms, where h is equal to b minus a by 3, as it was in the Simpsons 1 by 3 rule. And there is this 3 by 8. So due to which this rule is called as the Simpsons 3 by 8 rule. Inside of the brackets, you can see that the first and the last terms are with coefficients of 1, but every middle term is with the coefficient of 3. So which makes it rather simpler than the Simpsons 1 by 3 rule. Because in the Simpsons 1 by 3 rule, we have to remember the coefficients will alternate between 4 and 2. 1, 4 and 2. Okay, 4 and 2, 4 and 2. But here there are we are only using the coefficients 3 and 3 over here. Okay, so h is equal to b minus a by 3, which is same as it was in the Simpsons 1 by 3 rule. Next is the yeah, and then of course it is more accurate than the Simpsons 1 by 3 rule. So you can see that it's because of this larger denominator in the Simpsons 1 by 3 rule. This denominator was 2880, but here it is 6480. So it gives much smaller error compared with the Simpsons 1 by 3 rule. So Simpsons 1 by 3 and 3 by 8 rules can also be applied one after the other. And then there are certain advantages of that. Okay, remember that we have the Simpsons 1 by 3 rule and we have the Simpsons 3 by 8 rule. Okay, so for the Simpsons 1 by 3 rule uh, can be applied. Okay, can be applied for even number of segments. 3 by 8 rule can be applied both for even and odd number of segments. However, we can also apply the 1 by 3 rule for one part of the segments in the same problem, and for the other part of the segments, other segmental parts for the problem, we can apply the 3 by 8 rule. So this also has some advantages. So this is the illustration of how Simpsons 1 by 3 and 3 by 8 rules can be applied in tandem to handle multiple applications with odd number of intervals. So in this case, we have the odd number of intervals, 1, 2, 3, 4, 5 number of intervals. So what we can do is we can apply the Simpsons 3 by 8 rule for the whole, or another option is that for the first 2 intervals, we can apply the Simpsons 1 by 3 rule, and then for the last 3 intervals, we can apply the 3 by 8 rule. Why will we do that? Well, in this case, you can see that the number of intervals are only 5. But for a larger number of intervals, say maybe which are in something like in hundreds or even thousands of intervals, the computational effort for the 3 by 8 rule is much higher than for the Simpsons 1 by 3 rule. So Simpsons 1 by 3 rule is also accurate. Okay. So therefore, we can apply more efficient Simpsons 1 by 3 rule in this case for the even number of segments, and for the remaining odd number of segments, we can apply the Simpson 3/8 rule to save on the computational efforts. Okay. So let's see the application of the Simpson's 3/8 rule. The same example, okay, from a is equal to 0 to 0.8. So in this case, now remember that for the single application of the Simpson's 3/8 rule, we need 4 data points, okay? So these 4 data points, then we can get from 0.2 to 0.8. So we can take 0.8 minus, if there are 4 data points, then that means there will be 3 segments, okay? So from 0.2 to 0.8, then we will divide by 3. So then we get these 4 data points. And what we will do is we will take this first value, then 3 times the second value, then 3 times the third value, and then the last value, okay, according to the formula over here. Yeah, according to the formula over here. So we will take this, and then we will multiply it by 3h by 8, where h is equal to b minus a by 3. So in this case, the simplified form of this will be, because in this case, for example, if you take h is equal to b minus a by 3, so this 3 will be will cancel with this. Okay, 3 will cancel with this. So it will be, if we will put h over here, so it will remain as b minus a divided by 8. It will remain b minus a divided by 8. So b minus a divided by 8. So this is how we will apply this formula, and then it will give us an answer of 1.51917. So which gives a true error of 7.4%, but to 7.4%. So which is more accurate than the single application of the Simpsons rule. Remember that for the single application of the Simpsons rule, we got a 16.5% error. It was in the example 21.4, right? 16.6%. Okay. So now in example 21.6, we got an error of 7.4%. Okay, so this was the part A, and then we can find its approximate error by the formula. In the second application of this example, we can do this also in conjunction with the Simpsons 1/3 rule. So in the Simpsons 1/3 rule, then what we will do is we will need, in this case, 5 data points. So what in this case we will need 6 data points, and then there will be 5 segments. So for the out of 5 segments, for the first 2 segments, we will apply the Simpsons 1/3 rule, and for the last 3 segments, we will apply the Simpsons 3/8 rule. So in this case, accordingly, we will get the points from 0, 0.6, 0.32, and 0.8. So 0.8 divided by 5, so that will be 0.16, and then accordingly we will get these points. So for the first 3 points, f0, 0.1, and 0.32, we will apply the Simpsons 1/3 rule. And then the last 3 points in which f0.32 will be common, 0.32, 0.48, 0.64, and 0.8, we will apply the Simpsons 3/8 rule. So here in this case, the integral for the first 2 segments is obtained by the Simpsons 1/3 rule. So here we can see that b minus a was 0.32 in this case. this because we are applying the Simpsons 1/3 rule for the first 3 points. So this will be A, this will be B. So 0.32 minus 0. Okay, 0.32 minus 0 divided by 6, and then first point 4 times the second point, then the last point. So it gives us 0.38. So this is just part of the answer. For the last 3 segments, 3/8 rule. So we will start from here, 0.32 to 0.8. So B minus A will be 0.8 minus 0.32, which is 0.48. Yeah, 0.48. And the first point, which is 1.74, first point was this. And then the second point multiplied by 3, third point multiplied by 3, the last point. So second point, third point, these will be multiplied by 3, and the last point. And divided by 8, because if we see that the formula was giving us 8 over here for the single application. Okay, so it will be 1.26. And now 1.26 is added to this 0.38. Then we will get 1.65. And this 1.645, and now we get an error of about 0.28%, which is even better than before. So it is better than the single application of the Simpsons 3/8 rule, right? It is better than, because in the single application of Simpsons 3/8 rule, we got a 7.4% error. But in this case, we got only 0.28% error over here. Okay, the hybrid application of the 1/3 and the 3/8 rule. So you can see that the hybrid application of these 1/3 and the 3/8 rule can improve the results even in the single segment applications. So if we apply the multiple segment applications, then we can even improve the results more. Okay, so these were the Simpsons 1/3 and the Simpsons 3/8 rules. So remember that we have discussed about the trapezoidal rule, in which there was only one segment. In the Simpsons 1/3 rule, there were only 2 segments. In Simpsons 3/8 rule, the minimum number of segments were 3 and the points were 4. So these 3 rules we have studied. However, there are even higher order rules as well, such as the Boole's rule, which has a segment of 4, and then another higher order rule which has a segment of 5. Of course, we are not looking at their applications over here, but these rules also exist. And then accordingly, you can see that their truncation errors are also reducing. Okay, truncation errors are also reducing. We can see it with the help of these higher values of the denominators. So all of these rules are called as the Newton-Cotes closed formulas. Okay, so the family of these rules is called as the Newton's Cotes closed formula. So Newton's Cotes closed integration formulas. So these formulas are presented in this format of this equation, so that the weighting factor of the data points would estimate the average height is apparent. So the step size is given in all of these cases. The step size is given by b minus a over n. Okay, the step size is b minus a over n, but which is given by h. So we have looked at the examples of these one type of the trapezoidal rule and the 2 types of the Simpsons rule today. And there is another application for the integration formulas, And that application is when the integration is with the unequal segments, with the unequal segments. So for example, I is equal to h1, fx naught, fx1. So in this case, we can only apply the trapezoidal rule. So we cannot apply the Simpsons rule for with the unequal applications. So we will look at these unequal applications in the next class. Okay, so I stop at this moment, and then we will continue this topic in our next class.